Okay, welcome to this math tutor training on radical expressions. We talked about rational expressions in the last video. Let's talk about radical this time. Radical means that there is some kind of root in it, square root, cube root, even something to the 1/5 power, right? Fractional exponents are really roots in disguise. So any of these would be radical expressions because they have those symbols. So let's start off with just numbers, and we'll add a few more variables in there. To simplify, just like with the last video, to simplify it always helps to factor first. So let's just start with the number 48. And we'll just start with the positive 2, a nice even 2. Divide by 2 again, divide by 2 again, divide by 2 one more time. And so the prime factorization is 4 2s and 1 3. Okay, with roots, however many roots it is, it tells you how many it needs to escape. Here's what I mean by that. The square root of 2 times 2 is the square root of 4, which is just 2, right? Or if you think about it as the square root of 2 squared, the root and the exponent are inverses of each other. And so we just have the base left, or 2. And the same thing happens here. 2 times 2, but these are all under the square root. And unfortunately, there is not another 3, so we have the square root of 3 will just remain there. And simplifying that even further, we have 4 times the square root of 3. You could also have started at the beginning. Maybe you said, okay, 16 times 3 is the square root of 48. Square root of 16 is 4. 4 root 3, either way you get it. However, if you have a different root, like a cube root, would tell us how many it needs to escape. It needs 3. Here's what I mean by that. Let's start with the 16. Break that down. Again, we have 2 times 2 times 2 times 2. Now I can't just take 2, right? I have to take 3 because the cube root of 2 to the 3rd power will give me just 2. So I need 3 in order to quote unquote escape the radical. And so I will still have underneath the radical that other 2, right? So cube root of 2 cubed gives me 2. I'm just going to leave some space over here. And then there's 1 left over. Same thing happens with this group of x's. We get 3 of them that come out into 1 just x, and then 1 x remains. With the y's, the cube root of y cubed is y. And with the z, we have z cubed twice, so each of those comes out of the radical. We don't have any y or z left in the radical. And so our final answer is 2xy z squared equals cube root of 2x. Not equals to, multiplied by, because that's still left over. So that's simplifying. Again, factor as much as you can, and then whatever kind of root it is will tell you how many there you need to escape the root. If it was that 1/5 or that 5th root, you would need 5 of that base or variable for it to escape the root. Alright, let's talk about adding. Remember from a video a long time ago that you need like things in order to add. The square root of 20 and the square root of 45 sadly are not alike, but we can try to make them that way. So if I simplify these, just like we're doing with the other videos, with the other problems, the square root of 20, I can break that down to the square root of 4 and the square root of 5, so that is 2 root 5. And then 2 times the square root of 45. Let's see, I'm going to ignore the 2 for now. Square root of 45 is 9 5. Oh, so that square root of 9 is a 3. 2 times 3 is 6. And I have a root 5, so now we have like terms, and I can combine them. Just as if it were 2x plus 6x, I'm just going to add the coefficients, or the numbers in front of the radical, and keep the square root 5 inside. Same thing would hold true for subtraction. You need to have like things, and you would just add or subtract with the numbers outside of the radicals. Alright, to multiplication, again, we don't need like things. We're just going to multiply everything together. We're going to multiply the square root of 5 times the square root of 7, but also times the square root of 1. It's going to feel like foiling or multiplying or box method. You can even use that here. Same idea as with polynomials. So the square root of 5 times the square root of 7, they both have the same square root, and so we'll combine those inside. Square root of 5 times 1 is the square root of 5. Square root of 6 times the square root of 7, don't lose that minus, it'll stay out front. Square root of 42. And then square root of 6 times 1, you can have a minus square root of 6 right there. We can try to simplify the 35 and the 42, but nothing else comes out of their square roots, so we're just done. Can't combine any more like terms. That is, simplifying, adding subtracting, and multiplying with radical expressions. Oh, rational, it's back. We're going to talk about rationalizing a denominator. So let's say I have something that looks like this. Oops, here we go. 2 over the square root of 5. Square root of 5 is not a nice rational number. We plug in the calculator, there's no end to it, and there's no pattern, and so it's not a rational number. We want to find a way to make it into a rational number. That's called rationalizing the denominator, meaning that there's no radical in the denominator anymore. So that can be with numbers or with variables, even if there's a square root of x down there. You can do something with that. Alright, so I'm going to multiply by something to give me a rational number on the bottom. There's already a 5, so what if it was a 5? So in order to get a 5, I need to multiply by its square root. Right? The square root of 5 times itself will give me 5 by the definition of what a square root is. But also with fractions, what you do on the bottom, you have to do on the top. So we have 2 root 5 there. So we just multiply until there's no square root there anymore. But what if it was a cube root? Alright, here's our process. Multiply by any form of 1 that will get rid of the radical. Form of 1 meaning you do the same thing to the top as to the bottom, just like with any fraction. Let's look at this cube root of 1/2. With any radical, you can split up between the top and bottom of a fraction. Cube root of 1 is 1. It's a nice perfect cube. But the cube root of 2 is just cube root of 2, irrational. And so what we need to do is we multiply by a form of 1 to get rid of the radical. So let's say we get cube root of 2. Let's see if that works. On the top we have cube root of 2. But on the bottom we still just have cube root of 4, which is still an irrational number. Because it's a cube root, it didn't just automatically get rid of the radical. We need, just like we said on the last slide, 3 of them. So we're going to do it again. And of course, if you wanted, you could also just multiply that by the cube root of 4, top and bottom in one step. That works too. So on top we have the cube root of 4, and on the bottom we have the cube root, I can't say it anymore, cube root of 2 cubed, or cube root of 8, which is just 2. Now remember, this is just an equivalent form of a fraction. If I plugged cube root of 1/2 and the cube root of 4 divided by 2 into a calculator, I get the same decimal answer. So it's just a different form of the same thing. But what if there is a plus or a minus in that denominator? If I just multiply by, like I was doing on the other problems, like the square root of 2, I would sadly have to distribute that to both the 2 and the 3, and I would still have a radical in the denominator because I'd have 3 root 2. What if it was the same thing, like we've been doing on other problems? The square root of 2 times the square root of 2, okay, that gives me just 2. The square root of 2 times 3, there is still square roots in there. If I multiply all that out, I'd have 6 root 2 in the middle. But if I had it so that these were a positive 3/2 and a negative 3/2, that's 0, no middle term, beautiful. So I actually need to multiply by everything the same, except change that middle term. Remember that from difference of squares with factoring, same idea. These are actually called conjugate pairs. And multiply by the conjugate. And what you do to the bottom, you have to do to the top. Let's go ahead and finish this problem. So on top, I'm just going to leave that factored out for now. We can simplify it later if we need to. Alright, and on the bottom, square root of 2 times square root of 2 is 2. My middle terms cancel out. And the last two terms are plus 3 times negative 3, so negative 9. Oh, this is going to be nice. I know I should have got that 7 out there. 7 divided by negative 7 is negative 1. So I have negative square root of 2 minus 3. The 7's are gone. If If you distribute that in, you get negative square root of 2 and plus 3. So actually rationalizing the denominator helped us to simplify that. So there's no radical in the bottom, and there's also not a fraction anymore. Very nice. Remember, when there's a plus or minus, you can use this conjugate, which is the same exact terms, but one has a plus in the middle and one has a minus. Those are conjugate pairs, difference of squares, same things, and it rhymes. All right, one more thing with the radicals. Let's talk about radical functions. We're going to try to graph this, and we'll talk more about this if you watch the 110 videos, if you do that training. But we'll start off with this because there's a little bit of it in 101 as well. So y equals, what am I doing? Y-intercept means x equals 0, and the x-intercept means y equals 0. So we're going to plug those in and solve. So for the first one, I love y-intercepts. Square root of x is 0 times 3 is still 0, minus 4 is negative 4. So my y-intercept is 0, negative 4. All right, x-intercept is a y equals 0. So we're just going to go ahead and plug that in and solve for x. Add 4 to both sides, divide by 3, and square each side to get rid of that square root. And you get x equals 16/9. So my x-intercept is 16/9 and 0. Okay, let's talk about these. We haven't talked about these in a while. Domain and range. Domain is putting in all of the possible inputs that you can put in, right? So all of the possible x values. Because there is just a square root, like it's not square root of x plus 2 or square root of x minus 2 inside the square root, the lowest thing that we can plug in is 0. We don't want any negatives under the square root because we can't graph those imaginary answers. And so my domain starts at 0 and goes all the way to infinity. Because 0 is the smallest x we can plug in, it also implies the smallest y we can plug in. When you plug in 0, the smallest y you get is negative 4. And remember with these that the the bracket tells you you include that number. We can plug in 0, we can plug in negative 4 for y, but we can't plug in infinity. So our graph, just to go over those, 0 and negative 4 is my y-intercept. My x-intercept is 1.7 repeating, which is 16/9, and it starts at 0 for the x values and negative 4 for the y values, and just goes up from there. There you have it, radical functions. Go ahead and watch the next video about our imaginary friends.